So, applications of exponential functions. This is why we get to this, right? It's to solve word problems. We do everything so we can use the whatever we learned to solve word problems. So remember that we are dealing with exponential equations, and we said that an exponential, what's special about an exponential equation? How do you know it's an exponential? If the exponent is a variable, right? So if your exponent is a variable, that means it's exponential. Right? So exponential relations are modeled by the exponential equation. So the formula for an exponential equation is y equals a b to the power of x. That's the equation for it. Okay? We're going to define what a and b are, because a and b are going to be numbers, and y and x, they're going to be your letters, your variables. Okay? So a is called the initial value. So that's your starting point. That's what you're going to start with. This is what your principle is. This is what, when you're doing your equation, you're starting with this, and then you're going to see what kind of changes you have. B is what we call the growth or decay factor. Okay? So we have two options. It's going to be either growth factor or decay factor. If b is greater than 1, so your base is greater than 1, what's going to happen is your graph is going to get bigger, right? And then if b is greater than 1, then it's going to model an exponential growth. And if b is between 0 and 1, so this should say is between 0 and 1, should say 0 is less than b less than 1, and that models decay. Okay? So, if I'm looking at an example here, y equals 1,000, 1.05 to the power of x, where's a, where's b, and what does it represent? What's your a? So the initial is 1,000. So you're starting with 1,000. Okay? And then where's your growth or decay factor? In the bracket. So this is your b value. And is it considered as a growth or a decay? Growth. Growth. Is it greater than 1? Yes. So it's called growth. Okay? Because it's bigger than 1, so this is growth. Okay? I want you to get a paper, okay? We're going to take note of what we do in grade 11. We're going to go over a review of the different types of exponential functions. Okay? There's 4 of them, and you need to know the 4 different kinds. And if you guys are working on exponential as well, you probably want to listen to that. Okay? So, exponential. So we have 4 different formats. The first format that we're going to talk about is exponential growth. And we use this one when we have a rate. Okay? We use this one when we have a percentage. So when our growth rate, when we have a growth rate. And that formula is, now the formula can be different depending on the scenario. Okay? So the formula can be y equals a 1 plus I to the power of x. Okay? You can see it also as if you're dealing with money, right? You can see it as the amount is equal to the principal 1 plus I to the power of n. Now, do these two look the same? They look, right? Yes, I use different letters just because I'm representing different things, right? In this case, the y value is my amount, is my final amount. In this case, my initial value is my principal, right? My x is the period, is the amount of time. So it depends on what your scenario is. These two equations are exactly the same. You're using different letters, okay? Now, with respect to the rate, okay, now what makes it growth is because you're adding 1, okay, because it's 1 plus the I. So I is your growth rate. I is, let's say, 7%, or I is 25%, or I could be anything, okay? So I is a percentage. When I put it into my equation, I have to put it as a decimal, right? So when I put I into my equation, I is going to be 0.07, or I is going to be 0.25, right? So in this case, your I is going, you have to divide your percent by 100 to find your decimal and put it in, right? Now when I put it in, what happens is I have 1 plus 0.07, right? Which is going to make it a growth, right? Because it's going to be 1.07, which is greater than 1, right? Now, so when you're reading the question and you're saying that you put $1,000 in the bank, and then the bank is going to give you 8% compounding annually for 10 years, right? So this is a growth because the money is going to grow. Does that make sense to you guys? The other one would be exponential decay. Okay? Again, it's similar to the exponential growth. So you do need a growth or a decay rate, we call that, because it's gonna decrease. Now, what do you think the formula would be different than the growth rate? It will be minus I, correct. So the formula is going to be exactly the same thing. So it's going to be y equals a1 minus I to the power of x. Okay? So if your question is saying it's decreasing or decaying, you're going to be using this formula, the 1 minus the I. Again, I is your rate, so I could be 10%, I could be 5%, I could be whatever percentage it is. Are we okay with that? Yes? Now, these are the formulas that we use for exponential growth and decay. Then we have the ones that are special cases. Okay? So if the question says you're doubling or half-life or things like this, we have special cases formula for these. Okay? So if the question is saying then the formula is y equals to A as your initial. Because it's doubling, my base is, doubling means 2. So my base is 2. Okay? Because it's doubling, my base becomes 2. Okay? And then my exponent is x over the doubling time. Okay? So A is your initial amount. That's not going to change. Okay? X is the time. So X is going to always be a variable. And then D is your doubling time. Now again, guys, this formula can be written as A equals A0 2 to the power of T over D. It's still the same format, right? A is your final amount, A0 is your initial amount, T is your time, D is your half time. So no matter what letters you use, it's still the same formula, okay? You might see multi-variation of this formula that means exactly the same thing, okay? Now, let's look at an example that would deal with doubling and see where each letter goes, okay? So you have a bacteria count of 100 bacteria, and the count is doubling every 5 hours. This is a question. Find an equation that represents this question. And the count is doubling every 5 hours. Or the number of bacteria is doubling every 5 hours. So what's my initial count?
100.
And that goes where?
Where your A value is.
Where my A value is. Y is going to stay Y. My A value is 100. How do I know it's doubling?
Because this is doubling.
It says doubling. So this is how I know that I'm going to be using this formula, right? So it's going to be base of 2 to the power of what?
5. X will be 5. Don't we have to do every 5 hours?
So 5 hours represents what? What time?
The double time. So
The
D.
doubling time. Every 5 hours, it is going to double,
Yeah. So
right? So this is your doubling time, which is your D. X is going to have to stay X unless I say, how many bacteria do you have after 24 hours? Right? Then you put 24 for X and solve for it. X is your variable, right? Otherwise, it won't be exponential. Because remember, exponential means the exponent is a variable. Does that make sense? Okay? So in this case, this is my equation. Now later, I can answer this question I asked you. How many bacteria will you have after, as I said, after 1 day, which is 24 hours? You're going to have to put 24 in for X and then do the math. Okay?
Can you write that down?
You want me to do that question? Okay, so how many bacteria will you have after, let's do it after 1 day, okay?
That would be tricky like that.
Tricky. Why is this tricky?
Well, because if you're writing 1 day, but you're not going to substitute 1, you're going to put 24 hours.
That's right. My units have to match, right? If my exponent is divided by 5 hours, I can't put a day over 5 hours. I have to change the day count to how many hours in the day, okay? So that means I have to replace X with 24. Sorry. Okay? Because 1 day, there's 24 hours in 1 day, and my units have to match. If this is in hours, then this has to be in hours. If the 5 is in hours, then x has to be in hours. Does that make sense to you? Okay? Now on the calculator, you're going to have to enter it properly. Let's see what you guys can do.
Oh, man. It's wrong.
I don't know how your calculator works, but I would put 24 over 5.
How do I make the exponent of fraction?
So when you put your exponent, put the exponent, and then put that
You know what fraction was it?
fraction. Yeah.
Oh, yeah.
2,785 bacteria.
Calculator ever. Wait, what did you get?
Does it make sense? Yeah, because how many times is it going to double in 24 hours? So it's going to double about 4.5 times, 5 times, right? So 100 to 200, that's one time. 400, that's the second time. 800, 1600, and then double 16 is 32. So it's in between the 16 and the 32. Okay? Because there's almost 4.5 periods per day.
How would you put the other one in the calculator, the first one?
Which one?
The first 100, the first question.
This one? You can't put it in the calculator because you have an x.
Yeah, but how would that's just the answer right there?
This is what you have to put in the calculator.
No, see how you have the first question? Like, how would you solve it?
Which first question?
This question right here?
You can't solve that. This is an equation where you have to write it like this, and then if I give you x value, if I give you the time, then you can solve. Okay? So the only one that you can solve is the second part. The first part, x is an x. X could be any number. X could be any number. There's no, this is the equation. Equation has to stay with y and x. Are we okay with this?
All right, so for that, that's as far as it goes?
For that, and when I ask you to write an equation, that's as far as it goes. So the question for this would be, write an equation to represent this scenario. Right? And when I ask you to write an equation,
Unless we're given an x value.
yeah. So first, I will always ask you to write an equation to represent the scenario,
Right.
right? Or the situation, right? So that would be your equation, right? Equation should always have a y value, an dependent variable and an independent variable.
What if you give us y but not x?
Then this is solving, and then we'll do questions like this, and then you have to isolate. Then you have to isolate for x, and then you have to do the log. We'll talk about this. Okay? All right. The other special equation, so the special equation so far is this one, right, which is the doubling one. And then we have the half-life. So it's like when you have a piece of paper and then you're cutting it in half, okay? Or when you have a chemical and then it's decaying by half, okay? So it's a half-life, so we know that we're losing half of the amount every single period, okay? You see a lot of these questions in chem and bio, okay? So if I have the half-life, the equation is y equals, again, A, since it's half-life, what do you think my base is going to be?
2.
Oh, half.
What?
Life. Half-life, what would my base be? What would be my, whatever I put in the bracket here?
One.
Yeah, 1/2. Half. Why do you say 2?
Okay, I thought you meant divided.
Oh, okay, now I see what you're saying. You're telling me about the denominator.
Exactly, Glenn.
Yes. Okay, so my base is going to be a half. Again, my exponent is going to be x over something. Now, because it's half-life, we use the letter h, but h and d, they represent the same thing. D is the doubling time, h is the half time, or the half-life. Okay, so this is the half-life formula. Again, A is your initial amount, and then h is your half-life time. Okay, so h is your half-life time. So in the question, it will be carbon 14, whatever, something like this, right? Where you have 100 grams of carbon 14, and then carbon 14 half-life time is every 1,000 years, right? Things like that. So. How many of you saw something like this before? Carbon 14, the half, I'm just gonna give a number. The half-life of carbon 14 is, give me a number, big number. 54 years, sure. Write an equation that represents the situation. I know my writing is so nice and pretty and organized. Just remember that I'm coming up with this on the spot. Okay, so how would I write this?
So A 100 grams,
A is 100 grams, yeah?
and your H is 54 years.
Yes, because it's decaying half-life every 54 years, so this represents your H, right? So the Y is equal to 100. What's my A? What's my base, sorry? 1/2, and I know that because it says half-life. So if you look at this, it says half-life. And then to the power of x over 54. And that would be your equation. Are we okay with this? Now, what would be an addition, part B question for this?
You would give us an X value and be like, how much is it after
100.
100 years?
Okay, so if I say, I can say, how many grams of carbon 14 is left after 100 years? What do you plug in?
The X value.
The X value would be 100, and then you do your math. Okay? You can write that down if you want and then do the math. So it will be how many grams of carbon 14 do you have after 100 years? And then you can do the math. Okay?